Okay, so we'll do some examples, 2 or 3 examples. Maybe all in this lecture, maybe it'll spill into another one. So first one, we're going to just look at 2 independent gamma random variables with the same rate. We'll take lambda to be the rate, not the mean. So 1 over lambda is, well, the mean would be alpha over lambda and for x and beta over lambda for y, to be clear. And then we'll do this transformation. We'll make u be the sum, and we already know the distribution of u from, we did this with convolution last semester. It should be gamma as well, again with first parameter alpha plus beta and rate still lambda. The second one we don't know, and that's the one we're more interested in for this example. Say we let v be the ratio of x to the sum. What percent is x in that sum? Okay, so these are our transformations. So this is G1 and G2. And you see, we could write this down and we could write f of xy right now, but I think you know what those are, so we'll just get to that when we get to that. So we'll write that when we get to that. Okay, yeah, so okay, so is this 1-to-1? Sometimes it's a little hard to tell. If I take a pair, certainly if it was just this, it wouldn't be, but if I combine it with this, I think it is now 1-to-1, okay? So, so we're just gonna gloss over that at this point, I think. If you're not sure, make sure you convince yourself. And what's the support? The support would be all positive numbers or non-negative, so something like right? This is the support for either of them. No, this is the support for this, right? But not for this. What is the support here for UV? So this is for support for XY, or the PDF for XY. And for UV, V can't be bigger than 1, right? So for UV, it's 0, infinity, cross. I guess we could let it be 1 here. You can include 1 and 0 or not include them. It doesn't matter. Okay, so this is for UV. So A is not equal to B, but I believe the transformation is 1-to-1. Okay, so what are the inverse functions? This is not always easy to figure out. You have to solve a system of nonlinear, usually equations, but in this case, I think we can do it. What is the function? I'm sorry, how do I get back to x and y? So what is x? Well, I see x, if I multiply through by x plus y here, I have x is v times x plus y, and x plus y is u. So I know x is uv, right? So x equals, so these are my h equations that get me from uv back to x and y. And then what is y? Well, you could solve y is u minus x. So y is u minus uv, so that's u 1 minus v. I thought about this a little before I did it, so you know, maybe you don't see it right away, but you can get this. Okay. And v is between 0 and 1, and u is non-negative. J, what is the Jacobian here? I want the determinant. So first I take the x function, differentiate with respect to u, I get v, differentiate with respect to v, I get u. Take the y function, differentiate with respect to u, I get 1 minus v, and differentiate with respect to v and get minus u. So minus uv minus u 1 minus v. So that's good. I think this is going to cancel. So we get equals minus u. Okay, so we're ready to write the PDF down for uv. We have f uv little u v little v equals, let's first write this, the joint PDF of xy evaluated at x and y in terms of u and v, so uv u1 minus v, and then the absolute value of j, so we want times absolute value of j, which is just u. Okay, so this is what I need. If I know this, which I do, I have independent gammas, I know the parameters, so now let's write this down. So this is equal to, all right. Okay, so what do we have? We have the first one is gamma alpha. Remember, since these are independent, I can just write this as the product of the marginal PDFs. So the first one is lambda, the alpha. Let's write it a different way. So let's write, first one is lambda x to the alpha, so it's going to be uv to the alpha minus 1 times lambda e to the minus lambda uv over gamma alpha. And then the second one is, well, same thing, right? It's just lambda u 1 minus v beta minus 1 times lambda e to the minus lambda u 1 minus v over gamma beta, and then times u out here. Kind of a mess, but okay, it's not too bad. So need to collect the terms a bit here. So if I take my lambda terms, I have lambda beta minus 1, lambda to lambda the alpha minus 1, that's just lambda to the alpha plus beta. So we get lambda to the alpha plus beta. And in the bottom, I can see I have just this. And I have u to some stuff, and I should probably separate this out because I have this extra u here. So, and I have u is written as a factor very nicely. So I have u to the alpha minus 1 times u to the beta minus 1 times u. So that's u to the alpha plus beta minus 1. And for v, we have v to the alpha minus 1 and 1 minus v to the beta minus 1. So I have, yes, v to the alpha minus 1 and 1 minus v to the beta minus 1. And I'm still missing the exponential term, but the exponential term is e to the minus lambda u, e to the plus lambda v times e to the plus lambda v. And over here, I have e to the minus lambda uv. I'm sorry, this would be e to the plus lambda uv, e to the minus lambda uv. So those go away. So I just get e to the minus lambda u, I think. Yes. Okay, and this is just for, this is for v between 0 and 1 and u greater than 0, as we said above, and 0 else. Okay, so for u greater than 0 and 0 otherwise. Okay, well, that's it. We completed the transformation. We found the joint PDF. Thing to do next is if we want to see, say, we want to see the, say we want to see the, the marginal distribution of V, the ratio of X to the sum, then we have to integrate out U. We should do this. So to get the distribution for just V, we want the marginal distribution. So FV of little v is equal to integral. I integrate over all of U, and I just put in FUV. Okay, yep, true. I got to put all this stuff in here now, but a lot of this will come outside, right? I just have to put in what has U in it here. The rest is constant here. So this is just equal to, let's see, let's take out some of this stuff. So let's take out, the V's can come out, right? So I have V to the alpha minus 1 minus V to the beta minus 1. And I'll take out gamma alpha, gamma beta. They might have to go back in, I don't know. And let's see. Is this good? Let's see. Yeah, let's leave the rest in. So then I have 0 to infinity, and I have e to the minus lambda u. Yeah, this is right. So I have, I can write this like collecting these with this in a certain way. I'll put 1 lambda here with this, right, and leave the rest here like this. So I can write this lambda u alpha plus beta minus 1, and then lambda e to the minus lambda u du. And this you recognize is just the gamma function, right? This is gamma of alpha plus beta. So this is a nice result, right? So the whole thing is equal to gamma alpha plus beta over gamma alpha, gamma beta, times v to the alpha minus 1 minus v to the beta minus 1. And so, and this is for v between 0 and 1. So we see v marginally has a beta distribution with parameters alpha and beta. Okay, so what were we taking? The ratio of x to x plus y, and we get a, yeah, and they remember both x and y had the same rate parameter, and so we get a mean for v, the ratio of alpha over alpha plus beta. This makes sense when you think about the gamma in terms of sums of independent exponentials. Then if you have a sum of alpha exponentials over the sum of alpha plus beta exponentials, and they're all the same rate, you do expect the mean to be alpha over alpha plus beta. Okay, but it's interesting, and now you have shown this. All right, let's see, there's like 3 more examples I want to do. I think maybe we will do it in a separate video.